All right. We are going to apply these molecular orbitals for determination of the molecular term symbols. But before we do that, let us consider an example about the classification of the atomic orbitals according to lambda types. So here, 5d atomic orbitals. These are dx square minus y square, dx times y, dy times z, dx times z, and dz square. Classify according to sigma, pi, delta, etc. types. It is important to define the names of the axes. For a diatomic molecule, the z-axis is always the molecular axis. So if this is A, this is B, this is Z. X and Y axes are perpendicular. Say this on the blackboard, this axis is X and the perpendicular axis is Y. Okay. Now let us consider dx square minus y square atomic orbital. Its graph is drawn using the xy axis and the cross section here. And the graph of dx square minus y square looks like this. Now imagine the origin as the center A. This is center A. What is the direction of the z-axis? Perpendicular to the blackboard, which means I have taken this and then just rotate it so that xy plane lies on the blackboard, and then z-axis is towards me. Now consider or search for zero planes, nodal planes, which contain the z-axis. Do you see any such plane? Notice that the shaded parts in the lobes indicate opposite sign than the ones which are not shaded. So whenever you go from minus to plus, you have to pass through zero, isn't it? Therefore, this plane here, which is at 45-degree angle from the y-axis, is this a nodal plane? It is a nodal plane because you see sign is changing from one side to the other one. Is there any such plane can you find which also contains the z-axis? There is one more, which is this. So these are nodal planes that contain z-axis. Z-axis means molecular axis. So far, how many nodal planes do we have? 2 nodal planes. Can we find a third one? Just by looking at the picture? No. We just stop here. So there are 2 nodal planes. 2 nodal planes. This means lambda is equal to 2. Because what was our definition? Number of such nodal planes is equal to lambda value. If lambda is 2, what is the type? Which one of these symbols correspond to lambda equals 2? Sigma is 0, pi is 1, delta is 2. So, now for this dx square minus y square atomic orbital on center A, we have found that lambda is equal to 2. This means that such an atomic orbital will make a contribution to delta type MO. Delta type MO. Similar atomic orbital on center B also have the same property. So it will also contribute only to delta type MO. Now, let us look at dxy. dxy, so this is delta, lambda equals 2. Dxy is atomic orbital is also drawn using the xy plane. The x times y atomic orbital has such a shape, similar to this one, but it is rotated by 45 degrees around the z-axis. Remember, z-axis is perpendicular. It is the molecular axis. How many nodal planes does this atomic orbital have? 2. It is exactly similar to that one. But the planes are different. And here, there is a, what is this plane? YZ plane. YZ plane, and this is XZ plane. There are 2 nodal planes. 2 nodal planes. This means lambda equals 2 or also delta. So dxy atomic orbitals contribute to delta type molecular orbitals, just like dx square minus y square. So this is delta. Now let us look at yz. YZ, imagine this is y-axis, this is z, and we are drawing a dyz atomic orbital on the yz plane. So attach a local axis here. So yz will look exactly similar to dxy, except that the plane is different. It's on the yz plane. And such a molecular orbital. Now, this yz, dyz on center A. There are nodal planes here. How many nodal planes? 2. But please note that to determine value of lambda, we have to include only those nodal planes which contain the entire z-axis. Now, this nodal plane, does it contain the z-axis? Is the z-axis on this plane? Yes. However, this one, it contains just one point on the z-axis. It doesn't contain all of the z-axis. Therefore, this is not included. You have to count only this one. Look, number of nodal planes that contain the z-axis, that's lambda. Z-axis is not just one point. Z-axis contains infinitely many points. All of those points must be on the plane that we are looking for. So here, only one nodal plane that contains the entire z-axis or the molecular axis. Therefore, what is the value for lambda? Lambda is 1. In other words, what type of molecular orbital will such atomic orbitals contribute? Pi type. These dyz atomic orbitals will contribute just like px and py type atomic orbitals, only to the pi type. Let us look at xz. We draw it if this is center A. This is x. We are looking at dxz. dxz looks like this one or dyz, but on the xz plane, its graph looks like this. This is the z-axis. So how many nodal planes of the required type does this atomic orbital contain? Only one, isn't it? Only this. This is which plane? YZ plane. So lambda equals 1, which means pi type. Finally, dz square. dz square, very crudely, if this is on center A, it has a positive lobe there and then a negative lobe. This is center A. This is dz square. Now, if you look at this atomic orbital, and this is the z-axis, molecular axis, can you find any nodal plane which contains the z-axis? There are no such nodal planes which contain the z-axis. There are nodal planes here, from here to there is a sign change, but such nodal planes or nodal surfaces do not contain the molecular axis, so they are not included in counting. So here, lambda equals 0. If lambda is 0, it means sigma. So dz square atomic orbitals contribute only to sigma type molecular orbitals. In general, when we construct molecular orbitals from atomic orbitals, we first classify each atomic orbital to be used according to their lambda values, whether sigma type pi type, delta type, and so on. For example, up to now, what did we learn? S-type atomic orbitals contribute only to sigma-type MOs. PZ-type atomic orbitals also contribute to sigma-type. And here we have learned DZ square atomic orbitals contribute only to sigma-type MOs. Now, PX and PY type atomic orbitals contribute to pi type molecular orbitals. Also, we have seen here dyz and dxz, they also contribute. Which was it? YZ and XZ. They contribute to pi MOs. And as we have seen here, dx square minus y square and dxy contribute to delta type molecular orbitals. In other words, in an LCAO expression for a molecular orbital, which is, say, pi type, you see only such atomic orbitals, px, py, dyz, dxz. You do not see s-type or pz type or dz square atomic orbitals. Now, let us continue with electron term symbols of homonuclear diatomic molecules. Let us start by showing the relative energies of the molecular orbitals we have constructed so far. This is the lowest energy sigma orbital, and this is the antibonding. Next is, this is 1s, this is 2s A, 2s B, and here 2 sigma G, and second sigma U antibonding. And for the p-type atomic orbitals, there are 3 of them. These are 2p on A and same energy 2p on B. These are isolated atomic orbital energies. We have a, now remember, this is an important rule. The total number of atomic orbitals which are used to construct molecular orbitals, in this case, 3 atomic orbitals on center A and 3 atomic orbitals on center B. The total number is 6, 3 plus 3. Using 6 atomic orbitals, we construct exactly the same number of molecular orbitals as we have done shortly before. Now, of these orbitals, the lowest energy orbital we will assume is 1 pi u. Next one is the sigma type orbital constructed from the PZ atomic orbitals, and 3 of them are antibonding. The antibonding pi molecular orbital is lower in energy than antibonding sigma molecular orbital. Okay, so far 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 molecular orbitals here, and using these 10 molecular orbitals, we may examine the lowest energy configuration of second row diatomic molecules. Of homonuclear diatomic molecules. In other words, we are interested in finding this capital lambda, parity, and spin multiplicity. P is G or U. Parity. Lambda, capital lambda, is coded with a capital Greek letter, sigma pi lambda values 0, 1, 2, 3, etc. The letter codes are sigma capitals, pi, delta, phi, etc. Capital letters. Because we are term symbol, molecular term symbol means the overall term for the molecule containing many electrons. Now, in determination of the molecular term symbol, lambda value and S value, we proceed very similar to what we did in the case of atoms. We first define molecular shell. This is a group of molecular orbitals with given n, lambda, and parity. For example, a sigma shell, say 1 sigma or 2 sigma, any sigma shell, maximum occupation number of a sigma shell is 2 because there is just one orbital, molecular orbital here. On the other hand, a pi shell has 2 molecular orbitals. Each molecular orbital can occupy maximum of 2 electrons. Total number of electrons in a pi shell will be 4. Similar to what we did in the case of atoms, closed shells do not contribute to either total spin or the total lambda value. And parity of closed shells is always G. As in the atoms, non-zero contributions to S or to lambda is possible only if there are open shells in the electron configuration. Let us consider some examples. Lithium molecule. These are examples. There are 6 electrons. To write the ground electronic configuration, ground electron configuration, we start by taking the lowest energy molecular orbital, 1 sigma g, and use it for 2 electrons. This is now, is this closed or open? This molecular shell? Closed, because there is just one molecular orbital, and we are using it for 2 electrons. 2 is the maximum for a single molecular orbital. For the remaining electrons, we have to use higher energy molecular orbitals. The next molecular orbital is the antibonding 1 sigma u star. We also use it for 2 electrons because we are talking about the lowest energy ground electronic configuration. Is this molecular shell closed or open? Closed. These do not contribute to anything to S or lambda or to the parity. Now we have 2 more electrons. So the next molecular orbital is 2 sigma g. And we use it for 2 electrons. So, is this molecular shell, is it closed or open? Closed. All of them are closed. Therefore, no contribution to S. No contribution to S means S is 0. S is 0. If S is 0, spin multiplicity is 1. Parity is G. You can see it also from the configuration. 2 means G times G. G times G is always G, isn't it? Here also U times U. But U times U gives G. This is G times G, also G. Multiply all of them, G times G times G, you get G. This is what we mean by closed shells. Parity of closed shells is always G. So, lambda value as we said here, no contribution to lambda value means lambda value is 0. If lambda is 0, what is the molecular term symbol? Here, if lambda is 0, the molecular symbol is sigma. So we have sigma, multiplicity is 1, 2s plus 1 is 1, and the parity is G. Therefore, the ground electronic state of lithium 2 molecule has this term symbol. It's the singlet spin state, singlet sigma G. Let us also consider some low-lying excited levels. The last occupied or molecular orbital was 2 sigma G. If we, it is the highest occupied molecular orbital in the ground electron state, HOMO. For lithium, this is HOMO, this is LUMO for lithium. If we excite one electron from HOMO to LUMO, we get an excited electron configuration. Then we will have from 2 sigma G. So we have one electron left, and then we excite it to 2 sigma U star. That's an excited electron configuration. Now, is this open subshell? 2 sigma G, there is only one electron. What's the maximum? 2. So there is less than maximum, which means open. This is also open subshell. These are going to contribute to the S value and lambda value. Let us erase this part. There are 2 open shells. Each with 1 electron. So both S equals 0 and also 1 possible. Both S equals 0 means singlet spin. S equals 1 means triplet spin. Both of them are possible. Now let us determine lambda. Lambda values will arise from just these 2 factors. Now, sigma molecular orbital has m equals 0. Both of them are sigma. In a product, to get the total lambda, we are adding small m values for each orbital in the product. So m is 0 for this orbital, m is 0 for this orbital. 0 plus 0 gives 0, which means lambda is 0 for this electron configuration also, because these are sigma molecular orbitals. Next, parity. To get the parity, look at the parity of the first open molecular orbital, G, and the second one has U. It is G times U. What is the result of G times U? G times G is G. U times U is U. U times G is always U. So parity is U, which means we have a singlet sigma U term arising from this configuration, and also a triplet sigma U arising from the same electron configuration. So, if we draw the energy level diagram for the total overall states in lithium molecule, we are going to obtain the following. The lowest energy state the ground electronic state has term symbol singlet sigma g. These term symbols have higher energies than the ground. Now, which one is expected to be lower in energy if you compare just these two? One is singlet, the other is triplet. Please remember Hund's rule. Hund's rule says that among a group of similar states or terms, the one with the highest multiplicity is lowest in energy. So we expect triplet to be lower in energy. So the first excited state of lithium molecule should be a triplet sigma U state, and the next one should be the singlet sigma U. There are, of course, infinitely many others. So these are the first few electronic states of lithium molecule. Okay, we have one useful concept. We classify the electrons in the electron configuration into two types. The electrons in the bonding orbitals are called bonding orbitals. Electrons in the antibonding orbitals are called antibonding orbitals. All right? What is important is the net number of bonding electrons. These two electrons are bonding. These two electrons are also bonding. So total number of bonding electrons is 4. But there are two antibonding electrons. So we subtract 2 to get 2 as the net number of bonding electrons. This is also called bond or net number of bonding electrons divided by 2 is called bond order. So if there are, as a result, if there are just 2 net bonding electrons, and please keep in mind that a bond between 2 atoms is represented by 2 bonding electrons. So 2 net number of bonding electron means 1 bond. Bond order or number of bonds is number of bonding electrons over 2. This is the number of bonds. So in the lithium-2 molecule, therefore, how many bonds are there? Only 1 bond. There are 2 bonding electrons, but 1 bond. And this bond is a sigma type, sigma bond, as we see here. Now, let us consider boron molecule as another example. Boron. Here we have 10 electrons, ground configuration. We start with 1 sigma U star 2, that's 4. 2 sigma G, 2 sigma G, sigma U star 2, and then 1 pi U which contains 2, 4, 6, 8, 10. Okay. Let us start by considering bond order or number of net bonding electrons. Two bonding, two antibonding, they will cancel. Two bonding, two antibonding, they will also cancel. The net number of bonding electrons is how many? 2. Or bond order 2 over 2 equals 1. There is one, according to this discussion, there is just one bond in the boron 2 molecule, but it is interesting that the type of the bond is pi type, because essentially the bonding electrons are coming from the pi molecular orbital. Now, these are closed, but this is open or closed. How many pi-type molecular orbitals are there? 2 pi-type molecular orbitals. One is pi x, the other is pi y. Maximum occupation of a pi shell is 4. Here we have 2 electrons, therefore this is an open subshell, which means there are going to be contributions to S and lambda. Now, this is, represent this as pi 1 and pi minus 1. Instead of pi x, pi y, we can always use the complex molecular orbitals. Now, using spin diagrams, this is possible. This is the two spins are parallel, indifferent. Now, ms value is 1/2 plus 1/2. It is 1. And m value is 1 plus minus 1. It is 0. This means S is 1 and lambda is 0. So such a term symbol is possible, a triplet sigma. To determine the parity, we go back to this symbol here, 1 pi u times u, because there are 2 electrons here. U times u gives which parity? G, Gerade parity. In fact, there are several term symbols arising from this configuration, but all of them will have Gerade, because all of them have u times u symbol. There are also possibilities, other possibilities. The 2 electrons could be paired, spin paired. This configuration will give, this spin diagram will give S equals 0, singlet. M value, the first electron has small m equals 1. The second electron also have m equals 1. 1 plus 1 is 2. This gives lambda equals 2, or there is delta singlet G. This is also a possibility for the arising from this electron configuration. Finally, we have this one electron up spin, one electron down spin. This is also sigma, but it could be singlet sigma g. All of them have sigma g. So these are the possible term symbols. One is this, another one is that, a third one is this one. These are all arising from 1 pi u square open shell part. Among these three term symbols, which one do we expect to have the lowest energy? Please note that this, that, and that all arise from this electron configuration. They will have different energies. Which one is expected to be lowest in energy? Think about Hund's rule. What does Hund's rule say? Especially spin multiplicities are different here. Among the terms which arise from the same electron configuration, the term that has the highest spin multiplicity is lowest in energy. Therefore, the ground state of boron molecule is expected to be triplet sigma g. All right. This is the end of our discussion for the diatomic molecules. Next week on Wednesday, I'm going to discuss a little bit at least Huckel molecular orbital theory. Notes about Huckel has not been loaded into Otto class, but I'm going to load it. So it will be lecture notes 9. This is all about Huckel molecular orbital theory.